nonlinear sequencer is, how I came about the idea, and what it's supposed to accomplish. So first of all, this technique is explained in a paper that was published as part of the proceedings at the SEAMUS conference this year. And the paper is available. It can be launched directly from the launch patch of this package. It explains what a nonlinear sequencer is and all of the different ways of developing it. And it should clarify a lot of what I'm going to talk about today in case something is not clear. But in a few words, what a nonlinear sequencer does is mess with the time function of the sequencer. Instead of having a linear ramp that moves at a certain frequency in time, I can have a nonlinear ramp to trigger events at different rates in nonlinear fashion. Nonlinear sequencer explores this very idea of having mostly regular events and that are triggered at different rates based on a certain time function. But at the same time, to maintain a predictability of the sequencer. So one of the important feature of a sequencer is that it's very robust and predictable in its overall time management. I can have different sequencers synchronized and having a reliable rhythmic output based on if they're all based on the same clock, that is. So if I start changing the frequencies of different sequencers, I might get unpredictable results because the different sequencers might not line up anymore. So the nonlinear sequencer is supposed to fix this problem and have pretty much freely controllable management of this sequencer rate and function while maintaining overall predictability. This technique is computationally efficient and it's sample accurate. So it's all based on sample-based objects and can be relied upon for very good accuracy. There are two general ways to create a nonlinear sequencer. One is to create a distortion of the ramp itself, so to have the ramp not be a linear ramp, but it can be deformed by using what in sound synthesis is called wave shaping. So to have a lookup table from which the sequencer ramp reads from, outputting something other than a linear ramp, 0 to 1, which is not what we're going to talk about today. Today we're going to focus on the second case, which is what I call the fluctuating sequencer, which is a sequencer that has a variable frequency. So each ramp might have a different frequency, but this sequencer can be relied upon to wrap around a certain multiple of a fixed frequency. So what that means is to have a fluctuating frequency, so a frequency that changes over time, but that fluctuating frequency will eventually line up with a multiple of the constant frequency. And that's very important because in that case I can synchronize multiple nonlinear sequencers that have a fluctuating rate, and rely on their synchronization at a certain point in time. So how do we accomplish that? We accomplish that by creating for each frequency that I create as different from the constant frequency. I create a compensating frequency. If I have a frequency of 1 hertz, and that's my fixed frequency, and then I have a fluctuating frequency of 1.2, meaning it's faster than the constant frequency, then I just need to calculate a compensating frequency of 0.8 to compensate, and so that when I have 2 ramps at the constant frequency of 1, I can be sure that the fluctuating frequency plus its compensating frequency will be synchronized with 2 ramps of the constant frequency. So that will allow me to create oscillating, fluctuating frequencies, and yet have control over the overall behavior of the sequencer. So this will be this is simple enough in theory. To implement this in practice is it's a little more complicated, but I developed a set of tools to do just that, and that should make this idea accessible for different purposes. So the first object that I need to talk about is the fluctuate phaser, and the fluctuate phaser is that's what I just talked about. So here I have a random list that is output from my my random list subpatch, and I assume that my constant frequency, which goes into the second inlet of the fluctuate phaser tilde object, is 1, so it's a 1 hertz, and that will be my my green ramp is my constant frequency of 1 hertz, and then I have a set of fluctuating frequencies. So one is 0.81, then 0.98, and 1.46, and these are my random values for my fluctuating frequencies. And I can be sure that the green and the red phaser will wrap around after the length of the list of my fluctuating frequencies times 2. Times 2 because of what I just said. I need to calculate compensating frequencies for each of the fluctuating frequencies. So I built here a counter, and you can notice how it will synchronize after 6 ramps. The fifth is the sixth is index is the it will reset at 0. So if I change this value, now I have 5 ramps. I can count on this to be synchronized after 10 ramps. Let's see if that works. And it is. You can see how the red and the green ramp are synchronized just at that time, at that point. And the blue ramp, what the blue ramp does is just keeps track of the number of ramps that are being output, and gives me the wrapping around of that in a longer phaser sort of output. So the output mode of this object is a very important attribute, because that deals with how I organize the compensating frequencies and the fluctuating frequencies. So The first mode is the laced mode, where I have a fluctuating frequency and then a compensating frequency. This means that the synchronization point between the regular phasor and the oscillating phasor will be two ramps. No matter how long, how many fluctuating frequencies I have, I will have the frequency and the compensating frequency being paired, and so like they will be synchronized every two ramps. But then I have the delays, where I have all of the fluctuating frequencies and then all of the compensating frequencies. I have the scramble option, and I have the sort up, meaning I have like a sort of a accelerando, and then a retardando sort of effect, but always making sure that all of these frequencies wrap around my constant frequency times, I guess divided by the number of fluctuating frequency times 2. The group by attribute output mode gives me like a sort of laced delays mode, but instead of operating on the whole list, it just operates on sublists. So I have 3 and 3 here, 3 fluctuating frequencies and 3 compensating, and or 2, etc., etc. And of course, these should be multiples. The group attribute should be multiple of the length of the list. So this is just a way of demonstrating how this works, but where things become interesting in using the nonlinear sequencer is when I have actually more than one fluctuating phasor being operated acting at the same time. And I can see how here I don't have the constant frequency, but I have all just fluctuating frequencies, and they only wrap around after 6 ramps here. I can of course increase that. So now I have 5 ramps, which means after 10 ramps they will wrap around. And I made that clear by having this flashing yellow screen when that fluctuation comes to a sync point of all of the ramps. And you can see that also in the phasor, in the scope object that I created here, where they actually, every line is synchronized after 10 ramps in this case. So how do I use in practice, how do I use this fluctuating frequent sequencer? In general, I use always the same technique, which is to have a set of regular triggers. That's another idiosyncrasy of the nonlinear sequencer, is to use a regular pattern and then to have the nonlinear sequencer do the heavy lifting in terms of rhythmic organization. Of course, this might not be suited for a lot of the goals that you might be after, but if your goal is to create oscillations of rhythmic oscillations of different patterns, this might just be the thing for you. And to create a regular set of triggers, I created a pretty simple object that just outputs the name of the unique name of a buffer, and that name can be used to set a buffer playback object such as wave tilde, but can also be used with other objects such as play tilde or peak tilde. And these are all interpolating buffer playback objects. And so these the buffer with the triggers is contained into the object itself, the regular trigger tilde object. And what the buffer is just an empty buffer, except for samples set at 1 and equally distributed over the buffer itself. So I can have as many triggers as I want, and they will always be perfectly equally distributed along this over the course of the buffer itself. And every time I change the buffer, the number of triggers, which is the input that the regular triggers take, is just the number of triggers that I need. Then a new buffer name, again unique buffer name, will be output from its outlet. So I can just have a prepend set and then have a wave tilde object read from that. And the more than 0 tilde is given because of what I mentioned before. This is an interpolating playback object, which means that the sample that comes out of here might not be exactly 1. It might be something other than 1. And for some application of this technique, it might be important to have an actual 1 that comes out of here. So the more than 0 object just makes sure that the sample that comes out of here is always 1. And then I can use an edge tilde object to give me a max message, a bang, that can trigger all sorts of events once I use this technique. So the regular triggers is a pretty intuitive object that can be used in combination with a fluctuate phaser, but a more original and unique object of this package is the distance from pulse. So the distance from pulse is actually I think, pretty original idea, which is an object that gives me the distance that each trigger has from its regular peer. So if I have a regular pattern, and then I have a pattern that is distorted by the fluctuate phaser, for instance, rhythmically, the distance from pulse will give me how distant that particular trigger is from its regular correspondent. So in the first tab of the help file for the distance from pulse, I just built a proof of concept sort of or a demo sort of patch where I have two phasers that are perfectly synchronized, and I have the distance from pulse measure the distance. So if I turn the patch on and my two phaser are synchronized, then I can see how the distance is always reported at 0. And the third outlet gives me the index of the trigger. If I add a little bit of distortion in one of the two phasers, meaning I subtract 0.1 to the frequency, I can see how I start accumulating a distance. And this is how far the trigger is from its regular correspondent. And in this case, since they are always going farther apart, the distance will keep accumulating. If I reset it to 0, then it will always be 0 again. So this might not make too much sense in this particular setup. But if I bring it to my fluctuate phaser, which is uh, its the natural companion for the distance from pulse, then I can see how each of this distance will vary according to how far the trigger is from its uh, regular peer, and I could use this as a parameter to control pitch, accent, timbre of sorts, and this will make sense musically because it will play into a perceived sense of pulse that in this case is not explicitly declared because the fluctuations of the phasors are playing against the sense of a pulse. But this distance from pulse object can give me parameters that might subtly imply the pulse. For instance, adding an accent when the distance is it's not it's small, or deny that pulse by, for instance, adding an accent when the trigger is far from the pulse. And to make, since these values can vary arbitrarily, and it's hard to predict how they behave over time, I built the last object I want to talk about today, which is the running scale tilde object, and that's just a scaling object that has a simple machine learning principle inside, where the input minimum and the input maximum are changed based on the minimum and the maximum values that the running scale is receiving from its leftmost input. So in this case, if I go to the L file of the running scale, so the running scale object, it just adapts its low input value and high input value to the incoming values from the leftmost input. So if I, in this case, I have values that are between 5 and 10, as I can see from this scale. I'm just scaling this up to 5 and 10 as it shows in this number box here. But after my running scale operates, and I gave it arbitrarily small and big numbers as an initial value. So these are the input minimum and input maximum are not really important in this object. They are there as an initial guess of what the input minimum and input maximum might be, but the actual input minimum and input maximum will be adapted based on the minimum and maximum of the incoming message, on the incoming signal rather. So just like in the scale tilde object, I have an input minimum, an input maximum, and then I have the output minimum and output maximum, and just I can and then the exponential curve for the scaling. But differently from the scale tilde object, I cannot change the input minimum and input maximum because that's what the running scale is doing, is adapting itself to that to change those values. So this object is the last one I want to talk about, and finally what I have is my example patches. In this patch, I'm using the fluctuate phaser and my distance from pulse object. and use the values of the distance from pulse to create accents. And so I can have either accents that are given when um, when the when the trigger is actually close to uh, the um, the beat, and or I can give accents when the trigger is far from the beat, and this might be subtle, but the difference it's definitely there. So let's try to hear it. And I have here just a kick drum MIDI sound that gives me the beat, and I can turn that on or off. Let's see. This case is synchronized. As they go far away from the beat, they will be less loud. So let's try the other mode. So now I will have sounds that are louder when they are actually farther from the beat. This is the beat. And you can hear there is some sort of like expressive quality to using the distance from pulse as a velocity controller. And incidentally, I'm also using it to choose a certain pitch from a C major scale. That's less important. Uh, this is a little more, slightly more complex example where first of all I'm not using MIDI. I'm using a um, just a triangular wave, and I'm using the trigger to generate an envelope, and then the quality of the envelope is also controlled by the distance from pulse. So let's try. And the panning is also controlled by the distance from pulse. If you're listening to this with headphones, you will hear the difference in the panning. And you also might hear that whenever I change something, it might take some time for the running scale to adapt to the new value. Like now, the distance from the running scale is adapting, and it's outputting increasingly. I'll keep updating this package, and I'm curious to know what feedback you might have for me. And of course, any bug reports is welcome. And I will add the other technique of nonlinear sequencing described in the paper soon. So Stay tuned, and I hope you enjoyed this.